Friends of physics, welcome back. It's so good to see you again, this time for the closing ceremony of the 55th International Physics Olympiad. Yes, it is the moment to say goodbye. So let's end with style today in the stunning campus of Centrale Supélec. By show of hands, who was here for the first time in France? In sunny France? Yes, a lot of you. Perfect. Just like a week ago, I will be your host for the day. My name is still Anatole. I am still a public speaker and science communicator on YouTube. Nothing much has changed for me. But I have the feeling you are not the same. Because what a week it has been for you all. You have met people from all around the world. You have gathered lots of experience and science learnings. You have trained to keep focused, even with very little sleep. And you even spent a week without your phones. Congrats! I am sure this week has had an impact on the rest of your career, even if you don't know exactly how right now. Before starting this event, there is one key message I would like to tell you. This closing ceremony is, of course, the one in which the medalists are revealed. But I want to be clear, some of you will not have any medal at all, and this is perfectly fine. I'm not joking. Of course, you could feel some frustration today, but in France we say l'important c'est de participer, meaning it's the taking part that counts. The most important is not the medal, it's the week in which you have all been active participants. Every one of you, you have lived all the IPhO moments. And I will tell you, when I was a physics student, I was not even selected to participate. I was just not good enough to represent my country. So to all of you, you have our most profound respect. I would like everyone to applaud every participant. And now, let's begin. The first person I would like to introduce to all of you gathered here today and to everyone watching the live broadcast on YouTube is none other than the president of Paris-Saclay University, Mr. Camille Galap.
Good morning, bonjour, hello, bon dia, oui, guten tag, dobry den. Buongiorno, les Italiens, Salutche, Jonapot. Je vais essayer de. Bon dia. Bon dia. Konnichiwa. Konnichiwa. Sabara el Krar. Bonjour, voilà. Bonjour. Bonjour à toutes et tous. Voilà. Ladies and gentlemen, honored guests, I would like to warmly welcome Paul Stanley, Secretary of the International Physics Olympiad Secretariat, Rajdeep Singh Rawat, President of the International Physics Olympiad Secretariat, Olivier Ginès, Director General of Higher Education and Professional Integration, Caroline Pascal, Director General of School Education, Daniel Rouen, Vice President of the French Physics Society, Mr. Thierry Coulon, the President of Polytechnic Institute, and Laura Choba, Mrs. Joanne Meyer, Deputy Director of Centrale Supélec, the members of the Scientific Committee, our partners, colleagues, and friends, and finally, you, dear students. Welcome to the closing ceremony of the 2025 International Physics Olympiad. It's my great pleasure to be a part of this ceremony, and I must say I am deeply impressed to be facing such brilliant young minds. This week has been challenging for you all. 400 young scientists gathered here on what we call the Saclay Plateau. And it's no accident for that the first ever French edition of this Olympiad was held here. Why Saclay then? Because this place is to physics what Hollywood is to superhero movies. But instead of capes and explosions, we get equations on Nobel Prize. Bravo. You can applaud. We have one Nobel Prize here, Mr. Alain Aspect. You can applaud him. In 1946, Frédéric and Irène Joliot-Curie, who gave their name to the street behind us, planted the first cornerstone. Frédéric lobbied to install the newborn Atomic Energy Commission here, while Irène persuaded her colleagues to transfer a few laboratories. One lab became two became a department, then a faculty, and then chain reaction, literally. Université Paris-Saclay, our engineering schools, especially Central Supélec, we are today. We'll let Xuan tell you all about it in a moment. And of course, our partners at Polytechnic Institute Paris, we are the heirs of his legacy. Great minds have worked these roads. Some of them are members of the scientific committee, Pierre Agostini and Anne Ludier for their work at the French Atomic Energy Commission, Alain Aspect and Albert Fert. I have no doubt that some of you, young scientists, will follow their lead. Usually, when I speak of young scientists, I mean newly appointed researchers, around 30 to 40 years old. But you, dear students, have proven that talent has no age. I am certain this experience will shape you. I hope that what you will take home is not just a medal, but rather a great deal of memories. I hope you will remember how you shared a coffee with the student from across the world, how another lent you a pencil, how you stayed up until way too late with another, talking about physics, or more likely, talking about anything else. I hope you will take home a bunch of email addresses. Maybe your new pen pals will co-write a paper with you in a few years. Maybe they will just become your friends, and well, this also that this week was about. You have shared an experience with 400 other students. You have shown that the universal language is not English or Mandarin, but the moment we haze written at the same elegant proof. Science knows no borders is a common saying. You have lived it. I am not a physicist, but I know that in physics we speak of closed systems. There is no such thing in human endeavor. The energy you have exchanged here will radiate outward. In the classrooms you will return to, in the labs where you may work, in the policies you will someday influence. Because you are carry a responsibility, the analytical skills, critical thinking, and problem-solving abilities you displayed all week are essential not only for working in physics, but also for tackling our world's challenges. To those who will stand on the podium, wear your medals lightly. To those who will, empty-handed, remember that Einstein failed an entrance exam and that Vera Rubin's first paper was rejected. So I would like to congratulate all of you. You can be immensely proud to have taken part in this prestigious competition. I would also like to thank and congratulate the French Physics Society and the International Physics Olympiad Secretariat for organizing this French edition of the Olympiads. Of course, I would like to thank Institut Polytechnique of Paris for hosting the contest and making this event possible here, where physics is in our DNA. Thank you to all the teams, the volunteers, the teachers, and you can applaud them, and the mentors who accompany teams, the volunteers, the teachers, and the mentors who accompanied the students or helped organize this Olympiad. And a final thanks to Central Supélec for hosting this ceremony today. Dear Xuan, the floor is yours. Thank you very much.
Thank you, Camille Galap. For the next speakers coming up on stage, you can just say hello in one language, but thanks a lot. Now, please welcome the Executive Vice President at Central Supélec, generously welcoming us to their amazing campus for this closing ceremony, Mrs. Xuanmi Meyer.
Messieurs, Mesdames les représentants des ministères de l'Éducation nationale et de l'Enseignement supérieur et de la Recherche, dear guests from all around the world, dear students, it's a real pleasure to welcome you here at Central Supélec, a two centuries great place for engineering, for the closing ceremony of this International Physics Olympiad. These past days have been a wonderful celebration of science, of physics in particular, and of the passion, talent, and determination that each one of you has brought to this competition. By participating in these Olympiads, you have proudly represented your countries. But beyond national pride, you have carried high the flag of physics itself. You are ambassadors of curiosity, of rigor, and of discovery. Let me congratulate all of you on your remarkable achievements. This competition demands excellence, creativity, and resilience. And you have met this challenge with brilliance. French Nobel laureates in physics accompanied this event. Their presence is not only a recognition of your work, but also a powerful reminder that science is a journey that begins with curiosity and leads, sometimes, to great discoveries. Let them inspire you. I truly hope you will leave great memories of problems solved, of challenging faced, but also of friendships made. Keep going, stay curious, keep questioning the world around you. The world needs scientists more than ever to tackle the great challenges ahead: climate, energy, health, technology. We count on your ideas, your insights, and your drive. Thank you for being here. Thank you for inspiring us also. And now enjoy this closing event. Thank you.
Thank you, Xuanmi Meyer. As I have told you at the opening ceremony, the French Physical Society is the association which organized this prestigious event, hosted by France for the very first time in the country's history. It is my pleasure to invite to the stage their past president and now vice president, Daniel Rouen.
Monsieur le Président, Madame la Directrice, dear Raj, dear Paul, dear all. 2 years ago, it was in July 23, the French Physical Society was facing the challenge of organizing the IPhO 25 as requested by the two ministries of Education and National Education and the Ministry of Research and Higher Education. SFP accepted the task, I must say, with some apprehension, facing the enormity of the undertaking. Indeed, it has been quite a challenge, but here we are, and thanks to the dedication of the staff of the SFP, of the commitment of very large numbers of volunteers, and of also people from the society who didn't count their time, we have the weakness to believe that this strong effort was successful. I met several of you who apparently share this feeling. They have much appreciated the opening ceremony, and I'm certain they will appreciate as well this closing ceremony, where we will congratulate the winners of medals and everybody, of course, and special prizes, and attend Alain Aspect's eagerly awaited lecture. For candidates, even if some of the tests were especially Frenchy, I think of the one on the bubble of champagne, or simply unexpected with non-standard physics, like the Monde theory, I hope you enjoyed the whole program we prepared for you with cultural visits, discoveries of top-level French labs, cruise on the Seine, and among all, friendly exchanges between motivated young minds of different cultures. The partnership that allowed to build this amazing event has been long and somewhat painful, I must say, to mount, but at last it has been a great success. Thanks to all our partners, with a special mention to our diamond sponsors, Jane Street, QRT, and SquarePoint, and to the organizing partners, Ministry of National Education, Research and Higher Education, École Polytechnique and Institut Polytechnique de Paris, Université Paris-Saclay, and especially today, École Centrale Supélec. In the name of the whole SFP and its president, Elisabeth Giacomino, I want to say a great, great thank to all of the actors of this success story. First, of course, the volunteers, the markers, and the SFP staff, among whom Méline, Benedict, Alexis, Marine. Then sponsors and partners, I already mentioned that. And finally, we should not forget the science committee who prepared the test under the leadership of Yannick Almeras, and the organizing committee led by Pierre Chavel and Dominique Aubert with the professional support of Julia Roussel. They did a wonderful work. Please, applause. Again, congratulations to all the teams, candidates, and team leaders. It has been a real pleasure to welcome you in France for this wonderful adventure, mixing up top-level science, culture, personal exchanges, and friendship. Thank you very much.
Thank you, Daniel Rouen. The next person I would like to introduce to the stage is someone you have already seen at the opening ceremony. But given the fact that you have changed a lot in a week, he has new stories to tell you, of course. I am speaking about the president of the Permanent Secretariat of the IPhO International Board, Professor Rajdeep Singh Rawat.
Mr. Olivier Guinness, Director General, Higher Education and Professional Integration, Professor Camille Galap, President, University Paris-Saclay, Mrs. Swan Mayer, Associate Director, Central Superlec, Professor Daniel Rouen, Vice President, French Physics Society, Professor Alan Aspect, Nobel Prize winner in Physics 2022, distinguished guests, team leaders, observers, academic and organizing committee members, dedicated volunteers, and above all, dear student participants, a very good afternoon to you all. Today marks the conclusion of what has truly been an exceptional week here in Paris, a week which I think you all will agree with me, filled with intellectual challenge, intense excitement, and definitely a lot of cultural exchange. IPhO 2025 has been a landmark IPhO edition with a record 87 participating teams and 5 observing countries, making it one of the largest, and I think probably the largest in the IPhO history. And you have been the part of this. So I congratulate you all. Over the past 7 days, we all got to wrestle through some of the most exciting and challenging theoretical and experimental problems that were carefully crafted by the host academic committee. We also had the chance to experience the rich culture, heritage, and the history of France, from the majestic palace and the gardens of Versailles, and the artistic treasure of Museum d'Orsay, to the serene Seine River cruise through the most iconic landmarks in Paris. I hope these memories will stay with all of us coming from overseas forever. And of course, an event of this scale and magnitude is only possible due to the dedication and the tireless effort of many people and institutions. I offer my deepest gratitude on the behalf of the entire International IPhO Board to Dr. Yannick Elmeris and Professor Nicolas Schlosser. I hope I have pronounced the name correctly. The chair and the vice chair. The chair and the vice chair of the academic committee, and to Dr. Dominique Aubert and Professor Pierre Chauvel, co-chairs of the organizing committee, for their outstanding leadership and dedication that made this event a grand success. My sincere thanks also go to the professors, the teachers, and other members of the academic committee, not only for crafting rigorous, challenging, and thought-provoking problems, but also ensuring that the exams were conducted and assessed with fairness and precision. A special round of applause for the entire academic committee. I would also like to thank the team of volunteers and helpers who cared for the students round the clock, ensured a smooth and welcoming environment. A big round of applause for them as well. We are immensely grateful to our organizer, the French Physics Society, and all their organizing partners and sponsors. Their names are there. Maybe it's too small a font for to see you from behind, but I think you can. They were just mentioned just now. Special thanks to Huawei, the IPhO International Board sponsor, who generously sponsored and helped us to provide partial support to many a team participating in this year's Olympiad. Finally, to the students, whether you stand adorned with medal or carry quite fire of lessons learned, you don't know the results yet, but you will see it sooner or later, you all have already triumphed. Congratulations to all those who are going to earn medals later on and the honorable mentions. Your hard work, patience, and perseverance has brought you here and will have you earned a well-deserved recognition. to those who are not going to receive any medal, remember, what defines you is not a result, but your resolve to keep questioning and keep trying. The true value lies in the experience, as was mentioned by the host in the beginning, and in the friendship formed, and in the fire that has been ignited in your pursuit of knowledge. For many of you, this may be the defining moment in your academic journey, the one that will shape your path ahead in science, education, or beyond. I hope you all will leave inspired and be confident of your potential. So until we meet again in 2026 in Bucaramanga, I wish you all safe journey back home, not now, after the ceremony is over, on tomorrow. Safe journey back home and a future filled with peace, curiosity, and discovery. Thank you.
Thank you, Professor Singrawat. There is yet another person who would have loved to be there in front of you today. He couldn't, but don't worry, thanks to a very precise scientific invention, we will be able to see him and to hear him. We call this invention the video. Let's hear from the General Director of Higher Education and Professional Integration at the French Ministry of Higher Education and Research, Olivier Ginez. Video. Let's hear from the General Director of Higher Education and Professional Integration at the French Ministry of Higher Education and Research, Olivier Ginez.
Président de la Société française de physique, mesdames et messieurs les présidents et directeurs d'établissement, chers partenaires, chers enseignants, chers organisateurs, chers bénévoles et surtout, chers et chers participants venus du monde entier. C'est avec un immense plaisir que je prends la parole aujourd'hui pour clore ces 55e Olympiades internationales de physique. La 55e édition. C'est un beau nombre triangulaire et un palindrome, ce qui ne manquera pas d'amuser les plus férus de mathématiques parmi vous. Plus sérieusement, la longévité des Olympiades est impressionnante. Elle dit bien l'enthousiasme que la physique peut déclencher. Elle m'a d'ailleurs, moi aussi, animé durant mes années d'étudiant et je suis heureux de pouvoir partager ceci avec vous. Pendant ces 7 jours exceptionnels, 87 délégations parlant plus de 50 langues différentes, rassemblant 410 candidats et 280 encadrants, se sont affrontés dans une compétition d'excellence scientifique. Cette édition est un moment historique pour la France qui accueille pour la première fois les Olympiades depuis leur création. Cela nous comble de fierté. Chers participants, je tiens tout d'abord à féliciter chaleureusement chacun d'entre vous. Durant ces journées intenses, vous avez relevé des défis scientifiques passionnants. D'une part, des épreuves expérimentales. Vous avez observé et analysé des phénomènes grâce à des manipulations précises en laboratoire. Et d'autre part, des épreuves théoriques où vous avez modélisé et résolu des problèmes complexes, démontrant ainsi votre créativité et votre rigueur. Ces deux volets exigeants et complémentaires illustrent parfaitement la richesse de la physique. Une science à la fois empirique, fondée sur l'expérience, et conceptuelle basée sur l'imagination et la rigueur mathématique. Je souhaite saluer tout particulièrement l'équipe de France, composée de jeunes femmes et hommes âgés de 17 à 18 ans. En tant que pays hôte cette année, vous avez donné une occasion unique sur la scène internationale. Les performances françaises sont régulièrement saluées à l'international. Lors des 15 dernières éditions, l'équipe de France a remporté 5 médailles d'or, 39 d'argent et 21 de bronze. Un palmarès qui témoigne de la qualité de votre formation, de votre passion et de votre engagement. Le comité d'honneur de ces Olympiades rassemble 6 lauréats français du prix Nobel de physique. Leur présence symbolise la richesse de notre tradition scientifique et l'importance de transmettre cet héritage aux générations futures, parmi lesquelles vous vous trouvez, futures actrices et acteurs de la connaissance. Cette édition des Olympiades s'inscrit également dans un contexte très particulier pour la France et pour la science mondiale. Après l'année de la physique et en pleine année internationale des sciences et technologies quantiques, il est de notre devoir de souligner auprès du grand public les vertus formatrices et citoyennes de la physique. Le programme de votre présence ici a été riche et varié, avec des conférences, des visites culturelles, telles que la Cité des sciences et de l'industrie, le musée d'Orsay, ainsi que la visite de nombreux laboratoires. Je crois que vous avez vu un échantillon très riche de ce que la France a à offrir en la matière. Enfin, et c'est le point auquel je tiens le plus, ce rassemblement international incarne le rôle fondamental de la science comme pont entre les nations, favorisant le dialogue, la coopération et la paix. Au-delà de la compétition, les Olympiades ont surtout été pour vous, je l'espère, une occasion formidable de rencontres et d'échanges avec des jeunes du monde entier. Animés par un même esprit de curiosité et d'excellence, vous avez tissé des liens d'amitié dépassant les frontières, les langues et les cultures. Cette amitié n'est rien de moins qu'un des aspects de la curiosité scientifique qui fait avancer le monde et porte la promesse de le rendre meilleur. En France, nous souhaitons la placer au cœur de nos politiques de coopération internationale. À vous, jeunes participants, je dis, vous êtes les porteurs d'un avenir scientifique libre et responsable. Je remercie chaleureusement la Société française de physique pour l'organisation de cet événement, ainsi que toutes les institutions partenaires. L'Institut Polytechnique de Paris, l'École Polytechnique, l'École Normale Supérieure de Paris, l'Université Paris-Saclay et Centrale Supélec qui ont accueilli avec générosité les différentes étapes de ces Olympiades. Un grand merci à toutes les équipes bénévoles, enseignants et personnels dont le travail passionné a permis la parfaite réussite de cette compétition exigeante. Organiser un tel événement international est un défi logistique, humain et scientifique de grande ampleur. Grâce à eux, chers participants, vous avez pu vivre une expérience inoubliable dans les meilleures conditions. En conclusion, je vous invite à applaudir tous les participants, les accompagnateurs, ainsi que tous ceux qui ont contribué à faire des Olympiades internationales de physique 2025 un succès remarquable. Que ce moment exceptionnel vous inspire et vous accompagne tout au long de votre parcours.
Thank you, Olivier Ginez. I told you that video was a precise scientific invention. Huh? What a week it has been. We promised to offer an intellectually stimulating, profoundly human experience. We hope we have delivered. One thing is for sure, you certainly did. You have proven that science is a universal language. You faced challenging exams. You tackled complex problems, showcased creativity and scientific rigor, and explored the frontiers of physics. But it wasn't all equations and experiments. Let's relive some of the most defining moments of the week with a tailor-made video.
La France est très fière d'accueillir en cette année 2025 la 55e édition des Olympiades internationales de physique qui existe depuis 1967. C'est donc le ministère de l'Éducation nationale, de l'enseignement supérieur et de la recherche qui a confié à la Société française de physique l'organisation de cet événement majeur de la physique pour les jeunes.
Il y a un principe qui est celui d'une rencontre internationale d'une centaine de pays. Une rencontre de jeunes de moins de 20 ans, une rencontre également d'adultes qui vont accompagner ces jeunes, et ceci autour d'une discipline qui s'appelle la physique, qui vise à décrire le monde par des modèles.
C'est une occasion de mettre en avant les sciences, des enjeux des sciences, de rechercher de très bons profils scientifiques, mais après de mettre en avant donc, sur le devant de la scène des jeunes, ce qui potentiellement travailleront plus tard sur les sciences, et puis de faire de la publicité pour les sciences, et les sciences en ont besoin.
I like physics because things that happen every day seems easier when it's explained with physics.
I have a feeling of some freedom, like exploring the world around us.
C'est une première victoire que de parvenir à aller au-delà de l'ambiance internationale et ça montre par la physique, par les sciences, on arrive à fédérer entre guillemets différents pays.
De voir des jeunes de tous les pays du monde passionnés par le même sujet et pour faire de la science, et j'en suis sûr, au profit de la paix dans le monde, c'est quelque chose de fabuleux.
And once you start really interacting with people, you learn more about them, you learn more about other cultures, and people are just generally nice with you, you start to understand the true meaning of IPhO. It's not just about testing us in terms of physics, it's also about uniting us. As they said, physics can also bring people together.
The best experience is the opportunity to make friends with other countries, many chances to exchange culture and also discuss our common interest in physics.
I think that the slogan "Physics Beyond Frontiers" has two main interpretations. The first one is that anyone, regardless of their nationality, can do physics, and that the national borders and countries aren't an obstacle. The other one is that the frontiers mean physical achievements and records, and that the physics should always innovate, break these records, and improve our understanding of the world.
En tant que physicien, vous êtes nécessaire pour résoudre une grande partie des problèmes du monde du XXIe siècle.
On est dans un monde, on le voit tous les jours, un monde qui a besoin de sciences, de physique, de technologie. Les Olympiades, c'est les talents de demain, des rôles modèles internationaux. C'est la jeunesse qui est finalement la graine du futur qui se dessine. Donc c'est absolument nécessaire et c'est vraiment très très enthousiasmant. C'est que pour faire face à des défis de changement climatique, de transformation énergétique, de la santé, de la nourriture, la science est indispensable. Toutes les initiatives qui permettent de motiver les jeunes pour s'embarquer sur des carrières techniques ou ce qu'on appelle STEM, sciences, technologies, ingénierie et mathématiques, sont nécessaires et utiles. Je pense que ça participe à avoir de meilleures entreprises, mais plus globalement, ça permet d'avoir une société éduquée qui est capable de raisonner et c'est bon même quand on ne fait pas des sciences plus tard.
J'ai réuni un comité scientifique très varié, donc dans ses origines. Donc il y a des professeurs de CPGE, des professeurs d'université, des chercheurs. Donc j'ai croisé tout cela, tous les regards de toutes ces personnes et le travail a été collégial. Quant tout, il y a 5 problèmes, si on prend l'ensemble des épreuves. Et il s'agissait qu'il n'y ait pas un seul problème identique, autant sur le fond que sur la forme.
Les dernières épreuves sont imprimées à 5 heures puisque les leaders ont besoin de beaucoup de temps pour traduire et pour imprimer.
It's the first time I met this kind of problem because I have done some of the past IPhO problems and I didn't see this type of problem before.
I tried my best and I think I gave it all in the end.
Après 2 journées intenses d'épreuves à l'école polytechnique, les candidats retrouvent leur leader et c'est le moment de décompression.
I've never been in France and it's like wonderful cities, like a dream to be here.
I would say that being on this cruise is the best experience so far. We get to see the Eiffel Tower and the whole city.
It's like the only best way that allow us to see the whole city and the architecture and the famous building.
Nous sommes très heureux de pouvoir accueillir cette Olympiade de physique qui est d'abord une question de jeunesse. Ce sont les jeunes physiciens de demain et les meilleurs du monde entier. Mais c'est aussi parce que, vous savez, le 19e siècle, celui du musée d'Orsay, c'est un siècle de grandes découvertes, un siècle d'innovation technique extraordinaire. Et donc la science dure et les beaux-arts se sont mutuellement fécondés à l'époque d'Orsay. C'est ce que nous avons voulu illustrer en invitant les jeunes physiciens de demain à découvrir les collections d'Orsay.
I came here and I saw that it was way nicer than how I thought it would be, and I'm very happy to be here and to represent my country. It was a very nice chance to visit France and do the IPhO here.
Un autre aspect des choses, c'est la volonté pour nous, au travers d'un travail effectué par la Société française de physique autour de la place des femmes dans les sciences et plus spécifiquement dans la physique, de valoriser la place des jeunes filles au travers de 2 prix, un prix individuel, un prix de la diversité et un prix collectif qui vise à mettre l'accent sur les équipes, malheureusement pas assez nombreuses pour nous, qui présentent, je dirais, une représentation assez équilibrée entre garçons et filles.
Les parcours scientifiques sont aussi pour elles, ça les amène à des métiers qui apportent véritablement quelque chose à la société. Les scientifiques, dans leur laboratoire, ne sont pas forcément toujours au contact des plus jeunes, alors que ce sont des moments où détermination sur l'orientation qui démarre déjà.
Cette organisation réunit 1030 personnes, environ 700 candidats, leaders, observateurs, mais tout le reste sont des personnes qui, de près ou de loin, contribuent au bon déroulement de cette manifestation.
Nous sommes extrêmement reconnaissants à nos 50 partenaires qui ont contribué à assurer l'équilibre de cette entreprise. En particulier, nos 3 sponsors diamants, Jane Street, Cube Research and Technology, SquarePoint, et également nos sponsors platine, l'entreprise Thales, ainsi qu'un partenaire du secrétariat international des IPhO, Huawei. Merci à eux.
Congrats to all of you and congratulations to the video team who perfectly captured the spirit of the week. The next person I will invite on stage has an incredible life. Imagine setting up a groundbreaking quantum mechanics experiment to settle a debate between 2 scientists and determine who was right and who was wrong. Now imagine these 2 scientists are none other than Niels Bohr and Albert Einstein. And your discovery leads to new possibilities for quantum computation and cryptography. I told you his life was amazing. It's because he is amazing. This person is a professor at the Institut d'Optique, and in 2022, alongside US physicist John Clauser and Austria's Anton Zellinger, he was awarded Nobel Prize in Physics. Please give a huge round of applause to Alain Aspect.
Who is connecting me? When we tried, somebody was there to connect my computer. Which one is it? This one? C'est celui-là? Je ne vois pas l'écran très loin là. Ça, c'est moi. Well, when we make tests, it was working, so it's a person. C'est connecté, mais c'est vous qui n'envoyez pas la bonne image. C'est pas vous qui étiez là. Okay, it's really, I'm impressed to be in front of so many young people who are the physicists of tomorrow. Congratulations for having been selected as the best in your country, and it means among the best in the world. And congratulations also to your teachers who helped you to prepare for this very selective event. And of course, it has been told better than I am going to say now, but congratulations to the teams who have worked very hard to make this event this wonderful success. So to the teams who are young people, you are going to make, or probably you have already made friends from all over the world, And along the years, you will discover that it is a wonderful experience. It's a personal experience. But it has been also said in previous talks, it will be useful also for the peace in the world who unfortunately is not in so good shape at the moment. And we will need physicists to keep contact between countries which at the moment may be at war. Physicists will play a role in the future when this country have to restore their relationship, okay? So remember that and keep contact with your friends in opposite countries. You love physics, and physics will reward you because it's a fantastic subject, physics. Don't listen to people who tell you that physics is the science of 20th century and now it's finished. All experience in the history of physics shows that every few decades there is a major change, and this opens a revolution and which opens new perspective. It allows people to raise questions that you could not even mention before these revolutions. But between this revolution, don't think that it is not interesting. It's also extremely interesting to work with what has been already established and to develop new applications and new technologies. And this is why the title of my talk is about the two quantum revolutions, the concepts, but also the applications. And before starting, I want to say that it is my hero, Albert Einstein, who has really been involved at the starting of these two revolutions. And I make a little bit of advertisement for this book about Einstein and the two quantum revolution. It was published in French. It is translated in English, in Chinese, in Italian, and many other languages. And if you want to know more about the role of Einstein in these two revolutions, you can afford this book. It's really cheap. Yes. So in fact, the two quantum revolutions are based on two concepts. On the one hand, wave-particle duality for the first quantum revolution, and then entanglement for the second quantum revolution. And you see that in both conceptual advance, Einstein has been involved. Einstein had been the first to enunciate wave-particle duality, and he's the one who put his finger on the fantastic feature of entanglement. Okay, I'm going to have a so-called laser. Okay, see, this is supposed to be a laser. Okay, so let us start with the first quantum revolution. Young people, probably most of you know, but it may happen that not all of you, that why do we use the word quantum? Why quantum physics? Why quantum mechanics? Quantization means that some quantities, which classically can take any value, have a continuum of value of possible values. In the world of quantum physics, they can take only some specific values. Einstein was the first to enunciate that for light. He told us light that was considered for very good reason as a wave, that is to say, a continuous object, okay? Einstein told us in some circumstances, you also have to consider light as made of small grain of energies that have been called later the photon, okay? The idea of discontinuity. But Einstein was not stupid, okay? This is not a news, okay? You all know that. And Einstein knew that you also need to describe light by a wave if you want to be able to understand phenomena like interference and diffraction. And so Einstein, thinking about that, enunciated in 1909 the idea of wave-particle duality. An object can be both a wave and a particle, and he told us that in the case of light. Another aspect of quantization is the fact that, according to Bohr model, which was built in 1913, an atom also shows discrete possibilities for the trajectories of the electrons around the nucleus. You know, this is the Rutherford model for an atom. You have a nucleus which is positive, electrons which are negative, and the force between them is just like gravitation. It's in inverse of the square of the distance. And so the model is just like planets around the sun or like satellites around the Earth. But there is something special in this model. Only sun trajectories are allowed. For you can send a satellite at any altitude. It is not the case for the electrons around the nucleus in the Bohr atom. This is another example of quantization. Where does it come from? Once again, from wave-particle duality. Louis de Broglie, French physicist, in 1923 enunciated wave-particle duality not for light, but for matter, more precisely for electrons. He said, we all think that electrons are particles, but sometimes they will also behave like waves. And if they behave like waves, what will happen when they are here on their orbit, on their trajectory? Well, when you have a wave, the wave wants to come again in phase with it, which means that the length of the trajectory here has to be an integer number of wavelengths. And just by applying this rule, de Broglie could make sense of the conditions that Niels Bohr had guessed in a heuristic way. When a professor tells you heuristic, that means he cannot demonstrate it, okay? And so Bohr had guessed the right condition. Louis de Broglie shows where the Niels Bohr condition comes from. I like very much this photo. Look at them. Don't they look happy? I hope you are as happy as them. Look, this is Louis de Broglie. He has just discovered his famous relation, lambda p equals h. This is Erwin Schrödinger. He has just discovered the Schrödinger equation. And really they are happy, and during your life as physicists, you will be as happy as them. Before going to the second quantum revolution, I just want to show what I think is the most striking example of wave-particle duality. I like it because it was a demonstration which was done by my first PhD student, Philippe Grangier, in 1986. With Philippe, we claimed that we had been able to build a source sending one photon after another photon, isolated photon, one after the other one. You may think that it had been done for long. No, it was the first time everybody had built such a source, and we claim we had succeeded. But when you're a physicist, you not only claim things, you prove it. So what did we do for proving it? We say, okay, if really it's a photon, if really it's a particle, when it comes on the beam splitter here, which is like a piece of glass splitting a light beam in two, if it was a light beam, it would be split in two. But if it is a single particle, it will either go on one side or go on the other side. And we prove that by having detectors here, an electronic circuit which is called a coincidence circuit. This coincidence circuit is able to tell you that there is a joint detection here and there. And if it is really a particle, there is no joint detection because once again the photon goes either on one side or on the other one. We did the experiment and we found no coincidence. Now, taking the same source, the same beam splitter, rather than putting a detector here and there, we recombine the two paths. And you have done enough physics to know that this is an interferometer. And in an interferometer, when you have a light beam, the wave is split in two and recombined. And the probability to detect here or there depends on the path difference between the two arms of the interferometer. We change the path difference between the two paths of the interferometer, and we observed, indeed, that what we are expecting was happening, that is to say, wave split in two and recombined, and a modulation in the probability of detection as a function of the position of that mirror. But it was the same source, the same wave packets, which in the first experiment had behaved like a photon going either on one side or on the other side. And in the second experiment, this same wave packet was split in two and recombined. This is wave-particle duality. This is what is at the root of the first quantum revolution. The first quantum revolution was first a concept, wave-particle duality. And then it was scientific applications. People needed quantum physics to understand the mechanical properties of matter. When you talk to your aunt or to your cousin who say, well, what physics is good for? Tell her, do you know that quantum physics was necessary to understand why matter is stable like that? At the end of the 19th century, physicists knew that matter is made of positive and negative charges, and they knew that positive and negative charges attract each other. So why is it that matter doesn't collapse on itself if positive and negative charges attract each other? And the answer is quantum physics, wave-particle duality. It's because the electron is a wave that you cannot squeeze it to such a small dimension that you would have if it was collapsing. So with quantum physics, physicists have been able to understand the mechanical, the electrical, and the optical properties of matter. They have been able to make sense of exotic properties like superconductivity, superfluidity, but it's not enough. It was first conceptual, secondly it was scientific, but then it was technological. In 1947, the best physicists trying to understand how electrons move in materials invented the transistor. Transistor was not invented by a guy in a garage. It was invented by the best physicists of the epoch, okay? And transistor was invented in 1947. And then another decade, and they learned how to put thousands and then millions and maybe even billions of transistors on a single chip, and this is a computer, okay? Then, in 1960, physicists, once again, not a guy in a garage, physicists trying to really understand as well as possible how light is emitted by matter, invented laser. And when you have a laser, what do you have? You have highway of information through optical fibers. You cannot communicate with optical fiber if you don't have a laser. So when you have a transistor, computers, and a laser, you have the modern society of information and communication. You are too young to know that there was a day not so long ago, like 3 decades ago, where society of information and communication did not exist. It has been a real revolution in the society, a revolution as important as the one due to the invention of heat engines in the 19th century, in the end of the 18th century. So the first quantum revolution was conceptual, scientific, and technological. Let us go to the second quantum revolution. The second quantum revolution is based on entanglement. It is Einstein, with his colleague Podolsky and Rosen, who put the finger on the extraordinary properties of entanglement. What he found is the following. If you have 2 photons emitted, one to the left and one to the right, you have a pair of photons which can be entangled in polarization, and you write it this way. You know enough of physics not to be afraid by an equation, and I'm going to tell you what this equation means. When you have a photon, you associate to a photon a polarization. The polarization is orthogonal to the direction of propagation, which means that it is in a plane perpendicular to that direction of polarization. And when you have an object which is a polarizer, what happens? If you have a classical beam, if it is polarized along the vertical axis, it will go up. If it is polarized along the horizontal axis, it will go down. And if it is polarized at an angle, a fraction will go up and a fraction will go out. But if you have a photon, you are not going to have a fraction of a photon up and a fraction of a photon down. You will find the photon either up or down. And you repeat the experiment many times, and you can define probabilities to go up and down. And you have the essence of quantum physics here. You have a measurement which can give only two possible results, and what the quantum formalism allows you to calculate is the probability to go up and down. That state here is the combination of a pair of photons with two photons polarized vertically and two photons polarized horizontally. And the smartest of you will say, okay, this plus that, it makes circularly polarized photon, or maybe photon at 45 degrees. Not at all. It is impossible to factorize that state, so you cannot say the first photon is like this and the second photon is like that. You have a superposition of a pair like this and a pair like that. And this is as surprising, in a sense, as a Schrödinger cat, which is both dead and alive. And you are going to see that you have really strange properties as soon as you have a pair of photons like that. Because if you calculate the probabilities of detecting the photon in +1 or -1 channel, assuming such a state for the two photons, you can first calculate the probabilities. And the probabilities are quite trivial. 50% to go up, 50% to go down. So it's just like towing cosine. It can be as well +1 as -1, and the same on the other side. Big deal, you're going to tell me. Hold on. If now I look at the probability to get +1 here and +1 here for the same pair. You have a pair, you look at the result. What is the probability to have +1, +1? What is the probability to have -1, -1? What is the probability to have +1, -1, etc.? The result of the calculation is that if you get +1 on one side, you get +1 on the other side. Never +1, -1. This is what we call a correlation in the world, in scientific world. I call it also a tricky coin toss, because if somebody is tossing a coin here, and people here can check that it is random. And there another person is throwing a coin here, and people around can check that it looks totally random. And now the people who are in the back see if it is head here, it's head here, and if it is tail here, it is tail there, then you are going to say there is a trick. Yes, there is a trick. The trick is quantum mechanics. How to understand this strong correlation at a distance? As a physicist, when you want to make an image, the first good reaction is to look at the calculation and try to make an image of that calculation. The problem with quantum physics is that the mathematics of quantum physics is not in our ordinary world. It is in an abstract space called the Hilbert space. You will learn that. And the calculation is developed in that abstract space, and it is only at the end of the calculation that you can answer the question, what is the probability to get +1 here, what is the probability to get -1 there, and what is the joint probability. So really, it's impossible to make an image from that abstract calculation in our real space. But as one of the excellent theorists in quantum physics, Asher Perez, wrote in his book, quantum phenomena do not occur in a Hilbert space. At the end of the day, they occur in a laboratory. And I want to have an image in the laboratory. And for that, there is a possibility. And this possibility was exactly the one envisaged by Einstein, Podolsky, and Rosen. They say, look, if you have two particles, you send them away, and there is a strong correlation between the result here and there, it just means that from the beginning, there was a joint property to determine the result of the measurement. Makes sense, right? This is the idea of completing quantum physics by adding a supplementary property that would say, for this pair, it will be up, and for the other pair, it will be down, etc., etc. So it's a simple and convincing image, perfectly scientific image, the kind of image that medical doctors or biologists develop to interpret the strong correlation between twin brothers or twin sisters, same color of eyes, same genetic disease, etc. But Bohr did not agree. Niels Bohr said that you cannot complete quantum mechanics. What do I mean by complete? Maybe I was not clear enough. In quantum physics, all the pairs are described by the same state, the state that I wrote already, XX plus YY. But Einstein and company told us, no, look, some pairs are like that, other pairs are like that, other pairs are like that. And Bohr said, no, you cannot do that. If you do that, quantum mechanics will collapse. But you have to realize that it was not a demonstration. You may have heard that Bohr replied satisfactorily to Einstein in their debates. This was true for the debate of 1927 about wave-particle duality. But it is not true about the debate of 1935 on entanglement. The reply of Bohr is a philosophical reply. In fact, the problem boils down to the concept of physical reality. For Einstein, when you have an object, there is an ensemble of parameters which constitutes a physical reality, and that ensemble of parameters allow you to determine the behavior and the result of measurement of on that object. For Niels Bohr, you cannot define the physical reality without specifying what is the measuring apparatus that will measure the property. It's two completely different conception of the notion of physical reality, and in fact, the problem was boiling down to this philosophical debate. So what happened after the big discussion of 1935? Nothing. Nothing happened because on the one hand, young physicists were using quantum mechanics to solve many problems, interpret experiments in the lab, etc. But also one point should be clear. There was no disagreement between Bohr and Einstein on the way to use mathematical formalism, on the way to calculate the prediction of quantum physics in this or that situation. And so, for this reason, people did not care so much until in 1964, so almost 30 years after the debate between Bohr and Einstein, John Bell made a fantastic discovery. He discovered that what people thought was a philosophical debate, in fact, could be settled by an experiment. What Bell discovered is that if you take Einstein's point of view, and he wrote some mathematics which is quite simple, all of you can follow the demonstration of this simple mathematics, but I have no time to show it to you, but really it's high school mathematics. And Bell demonstrated with a very simple mathematical demonstration that if you take a model in agreement with Einstein's point of view, there is a limit on the correlation you can observe. And these limits are given by what is called Bell's inequalities. On the other hand, if you consider the Einstein-Podolsky-Rosen situation with the strong correlation between the measurement of polarization between the two photons in the XX plus YY state, these correlations are so big that they sometimes pass the limit set by Bell's inequality. which means that you can settle the debate by an experiment. You do an experiment in which quantum physics predicts correlation bigger than the one allowed by Bell's inequalities, that is to say, allowed by Einstein models. There were 3 generations of experiments. So Bell was 64. There was a first generation of experiments starting in 1972 with John Clauser in Berkeley, Francis Pipkin in Harvard, and at first it was opposite result. It was interesting. Then there was a trend in favor of quantum mechanics when Clauser repeated the experiment of Pipkin, and there was another player, Ed Fry, in Texas in 76. So the score at this point was 3 for quantum mechanics, 1 for local realist model of Einstein. But in fact, these experiments were quite different from the scheme I have shown to you. And so you needed several intermediate reasoning to compare the result of these experiments to the Bell's inequality. And this is why I embarked in 74. So this is John Clauser in his lab. And this is why I embarked in 74 in a new round of experiments that I did in Institut d'Optique here on the campus of Paris-Saclay. And the main effort, remember that, for people who are going to be experimentalists, the main effort was to build a source of entangled photon with unprecedented quality and efficiency. In physics, when you want to do good experiments, you need a good signal. And so I worked hard to have a source emitting entangled photon with a much higher rate and purity than in previous experiments. And with that, I could do experiment in schemes closer and closer to the ideal discussion. And so we could do for a first time this experiment, and you are going to tell me, but it's exactly that scheme. Yes, it's the schemes that I presented. For the first time, we could have polarizer giving indeed the +1 and the -1 result. Before, in the previous experiments, they only had access to the +1 result, and it demanded an intermediate calibration, etc., etc. But the most impressive experiment, the one which took me to Stockholm to receive the famous medal, is that one. John Bell has told us that to make a really convincing test, you would need to change the orientation of the polarizer while the photons were in flight, okay? But you know, in my experiment, the distance between the source and the detector was 6 meters, and it takes only 20 nanoseconds for light. So it means you must change the orientation of polarizer in a few nanoseconds. It could not be done, but what could be done, and this is what we did, was designing and developing and building a switch able either to let light go straight or to redirect light in another direction. If you put here a polarizer in orientation A, and here a polarizer in orientation A prime, which is different, if the switch is fast enough, this is equivalent to a single polarizer that you switch between orientation A and orientation A prime. We could do that. And what did it prove? It proved that until the last moment, the result can be as well this one or that one. And it is only at the very last moment that the decision is made. And this is called non-locality. I will come back to that in 1 minute if they give me another 5 minutes. I don't know who is chairing. There is no chair, so I can speak as much as I can. Thank you. There was a third generation of experiments. My experiments gave a result in 81, 82. There was a third generation of experiments starting in the 90s, okay? And it was a yet bigger progress in the source. My source was better than the one of Clauser. But then in the early 90s, they were able to build sources emitting pairs of photons by a nonlinear optical effect called parametric downconversion. The important point is the following. In contrast to my source, in which the photons were emitted in all possible directions in space, so I needed big lenses to catch the photon, etc. When you do it with nonlinear parametric downconversion, the photons are emitted in well-defined direction. So well-defined that you can inject them into optical fibers. And if you have an optical fiber, you can go far away. And for instance, Nicolas Gisin in Geneva introduces a photon at Cornavin, the station at Geneva, and he can make measurements at a few kilometers because he uses the optical fibers of the telephone network in Switzerland, or the internet network in Switzerland. Similarly, Zeilinger, he was in Innsbruck at that time, he did an experiment in which he also was repeating the experiment I had done in '82. He repeated by having time to really change the orientation of the polarizer with a random number generator, etc. Okay. There have been a lot of discussion, and at the end of the day, we have to accept that Einstein's point of view, Einstein's vision of the world, which is called local realism, has to be rejected. What does it mean? Well, Einstein himself told us, because he was reasoning ad absurdum. He was telling us, if I was not right, this is what you would have to swallow. Well, this is what we have to swallow. And these are words of Einstein. Either abandon the independence of the physical reality present in distance volume, and we call it quantum holism, or accept that the measurement on one side modifies instantaneously what you have on the other side. And this is what we call quantum non-locality. And in fact, these two different presentations of Einstein lead us to two kinds of applications of entanglement. The first one, associated to quantum holism, is quantum computing. The fact that in two objects you have more than in the sum of what you have in the first and what you have in the second means that there is more information. And this is at the root of the formidable capacities of the quantum computers when we have good quantum computers, which is not yet the case. Quantum non-locality helps us to understand some fantastic possibility of quantum communication, and I will just show you one, and you will understand why quantum non-locality is important. It's the story of Alice and Bob, two friends who want to exchange some message, and there is a spy, the eavesdropper, who want to intercept the message. And we know since Claude Shannon and his theory of information, nothing quantum in that, we know that there is an absolutely secure way of doing that if Alice and Bob have two identical random series of 1 and 0. Alice uses this to encode, and Bob uses this to decode. And so the problem boils down to distributing to Alice and Bob identical random series of 1 and 0 without the eavesdropper being able to have a third copy. Because if this eavesdropper have a third copy, then he can decipher the message.
Sorry, Mr. Aspe?
Yes?
We have 1 minute left, sorry.
Thank you. Maybe it will be 2 or 3, okay? You know. You don't know me. You know, if you want, I can make a vote. Do you want me to speak another 5 minutes? Yeah. It's called democracy. Swiss people call it a votation. So to distribute this this series of random number, in fact, they use a source of entangled photon. And so, you know, if Alice gets +1, Bob gets +1, if Alice gets -1, Bob gets -1, so they have the identical series. Why is it impossible for the eavesdropper to make a copy? Because of non-locality. Non-locality tells us that until the last moment, you don't know if it will be +1 or -1. It's not yet decided if it will be +1 or -1. So there is nothing to spy here. And these are the root of the method of cryptography by Arthur Eckert. I could show you other examples. Well, just by the way, you know, now our Chinese friend have source of entangled photon in a satellite, and they observe entanglement, and they can exchange key for quantum cryptography at more than 1,000 kilometers. Entanglement survives at 1,000 kilometers. Okay, to finish, the second quantum revolution is based on two things. First, entanglement. I already mentioned entanglement is extraordinary property. But second, and this is very important, it's only in the last decades that physicists have learned how to isolate, control, manipulate single quantum objects. Before the 1970s, quantum physics was only about large ensembles of quantum objects. But starting in the 1970s, it became possible to trap a single electron, single atoms, emit single photons, etc., and you have even quantum circuits which behave like individual quantum objects with superconducting devices. And so with this, you can really think of technologies. And so what kind of application? Quantum communication, I already mentioned it. Quantum computing, I already mentioned it. And perfect, it works. Perfect, maybe one day. What means perfect? No, nothing is perfect. Perfect means that you can correct errors. In all computing systems, you have error correcting. In classical system, you have error correcting process. Well, for quantum, they try to do the same. Finally, there is quantum metrology. It works. So, I told you, speaking about the first quantum revolution, that a full revolution is first a conceptual revolution, then scientific revolution, and then technological revolution that can change the society. The first 2 points are okay for the second quantum revolution. The concept is entanglement, scientific application. We have many scientific applications of it. What about technology? You may read in the news about quantum advantage. Usually when you hear about quantum advantage, people have in mind the fact that a quantum computer could make computation much more difficult than the one you can do with a classical computer. This is a face of the coin. But there is another possibility which I think is very important, especially for people of your generation who have to face the problems of the planet. There is a reasonable hope that a quantum computer could make calculations that you can do with classical computers, spending much less electricity. If this works, I think that kind of quantum advantage will be as important. Okay. Will we have it? Nobody can answer with certainty, but there are many national programs. Here I cite just Île-de-France, or here European or national French, but every country has its own quantum computing or quantum technological program. You have companies which have plenty of money, they also have a program in it. And there are many startups, I forget many of them here, and young people, this is a fascinating perspective to work in that. So if you are interested, don't hesitate to go into quantum physics and quantum technologies and quantum science. Thank you very much. Questions? Questions or no questions?
I'm very sorry, very sorry. But if you stay here, they could ask questions afterwards.
Okay. Thank you.
Thank you, Professor Aspect. Now, to give us a comprehensive overview of the scientific achievements and challenges at these 55th Physics Olympiad, let's bring up on stage someone who has been instrumental in shaping the academic rigor of the competition. He is the president of the scientific committee. Please welcome Yannick Almeras. Voilà.
Ladies and gentlemen, dear contestants of the IPhO 2025, we have all the excitement of discovering the final results of the IPhO 2025. Before that, I would like to emphasize that while the IPhO has been an adventure for you, it has also been one for us. This adventure began for the scientific committee in the early 2024 in complete confidentiality until the moment of the event. I don't know how to push, to click, to pass. Yes, you can pass the slide. Mysterious meetings took place, rich in exchanges of ideas and diverse proposals, in order to offer you the most appealing menu possible for the examinations. The work of the scientific committee exceeded our expectations. We were spoiled for choice when it came to putting together the content for the competition. I would like to give special thanks to the organizing committee for their collaboration, as well as to all the volunteers and technical teams who contributed to the scientific committee achieving its objectives. Thank you also to the Oli Exams team for their advice and their management platform for the Olympiad. For the next slide, I would like to remind you the unique process followed for the IPhO. The scientific committee prepared proposals for questions which were revealed and finalized through discussions during the competitions with the leaders. You, the contestants, took the tests, then a team of markers from the organization corrected the papers, and also your leaders. Following this, a day of moderation was held yesterday to agree on the final results with the aim of ensuring a fair assessment. Now that all the examinations are over, it's time to reveal the scientific committee. You can put the next slide. Here are the people who created and worked around the exams. I hope you enjoyed these exams. Some of them are here today on your right in this auditorium. They are here. On the next slide, you will see also other people. All the markers who worked on your papers during the moderation also with the leader. Now let's take a look at the overall results for each part and each examinations, which were the heart of this event. So on the next slide, you can you know the histogram, so the first question. in the experimental test concerned measuring an Earth's magnetic field component after characterizing a magnet. The score histogram shows that this question was relatively difficult, but some contestants were able to answer it correctly. Next, the second question allowed you to play with the sand, and the spread of the marks shows that it was discriminating. I hope this question will encourage you to experiment with simple things, as the physics behind them can be fascinating. Next, here are the results for the experimental test as a whole. If you look at it from a distance, you can see a rough Gaussian, but if you look more closely, you can see some remarkable performances by some contestants. Overall, this test enabled a good assessment of the candidates, even if the distribution doesn't extend to the golden score. All the candidates were able to come up with interesting ideas. That's great. Now, move on to the theoretical test, with the first question relating to the study of galaxies, in particular their mass distribution. You can see that the marks for this question are spread widely across the marking scale, with quite few excellent answers. As for the second question, things are somewhat different. It's not us, it's you. So, the second question examined a model of Koch's timepiece. There were very few calculations and a lot of physical reasoning, which probably explains this particular distribution of marks obtained. This question was clearly difficult for many, but a few contestants answered it very well. Look at the end of the histogram. Finally, the third question, which concerned champagne, the famous French drink, concludes the menu. You can see that physics is everywhere, from galaxies to in our glasses. This question allowed quick-thinking candidates to express themselves and produce some very interesting answers. Thank you for them. Thank for them. Then, here are the results for the theory test as a whole. You can observe a spread in line with the desire to discriminate against the majority of candidates. There were clearly some remarkable performances, so you can look at your right. And now, here is the result for the competition as a whole, summing the scores for the experimental and theoretical test. You can see the number of mentions, you can see the number of mentions and medals that will be awarded, as well as the corresponding grade thresholds. The spread of scores remained fairly satisfactory, even if the scale from 0 to 50 points is not fully explored. One candidate clearly stood out in this competition, but be patient before we tell who is it. Before concluding, the scientific committee would like to offer you a gift. You can test yourself on the backup question for the theoretical test we have chosen to reveal which could very well have been selected for the competition. You could have been on this question. You can have fun with the question entitled Strongly Correlated Fermi Gases. The subject is already available on the IPhO 2025.fr website. You can solve it on the way home. And to conclude, congratulations for all of you for your participation. You all deserve it. I wish you, young men and women, a bright future and hope you will use the scientific method to the best of your ability to meet current and future challenges. Enjoy the rest of the ceremony, everyone.
Thank you. Thank you, Yannick Almeras, for this precise scientific review. We will, I promise, we will very soon begin the medal ceremony, but just before, let's enjoy a moment of artistic grace. I am sure you remember the performance at the opening ceremony of Duo 2G from the contemporary dancers Eugène Lide and Angela Aiello-Tournay. This time, Eugène will dance with Lisa Berzin, a health student who continues her dance training alongside her science studies, showing once again that science and art can match perfectly. Both are members of the artistic collective called Son et Lumière, based in the city of Montfermeil in Seine-Saint-Denis. Please welcome Lisa Berzin and Eugène Lide. Thank you, Lisa and Eugène, for this breathtaking performance. Now it is time for the honorable mentions. When your name is called, please stand up and we will all applaud. Excuse me if I butcher your names, but I promise for the most difficult ones, I listened to your audio files of yourself pronouncing your own names, like the athletes at the Olympics, like the swimmer, Léon Marchand. But I will do my best. Let's try. So, if your name is announced, please stand up and we will applaud. Let's see the honorable mentions. Sorry, I just need to have a look at the screen. Yeah. Let's go. Haira Petian. Haruturnian. Tradel. Lorick. Frast. Fink. Mamadli. Khalil. Sadiq. Raman. Farbin. May. Jocelyn. Kristik. Begovic. Baturik. Petrov. Avendaño Contreras. Duplanchich. Ael. Santi Sebastián Sarmiento. Simonsen. Peterson. Bro. Jacobson. Kopinen. Dang. Mekvabishvili. Niku. Gretarson. Javier. Atmaya. Emil Bekov. Bratali. Jemel Janovs. Ugvalbergas. Medina Pelaez. Sandu. Orhip. Jankovic. Van der Gier. Van Igem. Stoyanov. Shmiarko. Bilal. La Forteza. Dizon. Warzino. Rebelo de Souza. Neves de Oliveira. Cuello Prata. Nezovic. Lazic. Lavrikova. Gasperlin. Garcia Torcedillas. Fahim Nur Muhammad. Lonert. Ismail. Bengtson. Hawat. Kmes. Shmachan. Abu Said. Salimov. Mamurov. Anagurdov. Aksoy. Sadulaev. Mamaniyozov. And the last one of the honorable mentions, Abdumalikov. Woo! Congratulations to all our honorable mentions. Next, to give our medals to our bronze medalists, I call on stage Dominique Aubert and Nicolas Schlosser. Our honorable mentions. I call on stage Dominique Aubert and Nicolas Schlosser. So you will see there are several bronze medals, but when you tell people you got bronze at the Olympiad, they will think you were third out of all participants, so don't say anything. For all our medalists, when your name is announced, come and join us on stage to receive your medal. The first bronze medal, and we will applaud you. Paez, Melkonian, Galstian, Chan, Werge, Suleimanli, Jafarli, Gabriel, Numanovic, Barbosa de Santana Neto, Nikov, Nikolov, Christophe, Arabov, Zhu, Gong, Karan, Andelic, Teis, Mishta, Kosata, Morild, Bon Hansen, Nael, Pisalo, Karonen, Kubica Jabri, Fieler, Zavakidze, Georgadze, Mintenko, Jugerman, Fieker, Corduban, Kagiampakis, Elekes. We will have the photo and then, yeah, perfect, perfect. I was at Elekes. Banks, Virwandi, Maulana, Orfa Alfarizzi. There is a bit of place here, if you want to make place for everyone. Should we continue? Do we have the place for the whole picture? Maybe the photographs can tell us. Do we have place a bit here? Maybe if you can go to the other side, so then we can, yes, to the other side, perfect. We continue. Vertucci, Roccaforte, Motese, Gariglio, Yegenberganova, Pshembayev, Kim, Anali Ulu, Abdiev, Koselevs, Karnitis, Hodosevich, Dexnis, Ng, Lei, Kerwei Han, Carson Taikar Singh, Mungtulga, Gambold, Deger Saikan, there is still some spot on the other side if you want. How are we with the medals? There are lots of candidates. Are you keeping pace? All good? Let's go. We continue. Stepanian, Podolski, Stoyanovsky, Neshekovska, Amid, Litwin, Yursak, Gosel, Tirukonda, Shivakumar, Al-Saleh. It's so beautiful to see all those flags. We continue. Alassane, Al-Arfaj, Slanina, Kubricki, Koval, Dudek, Miklavsic, Prado Izquierdo, Ligored Obede. Calderon Alba. Let's see. I am surrounded. Pierre, can we continue? Can we continue? Yes? No? Let's pause for a second. But I promise I will call all the names. Huh? Okay. I think, yes, I will continue so that we maybe will have a picture with all our bronze medalists. Sorry, we continue with Zhang, Reikmut, Premanut, Yamsiribul, Nuryev, Anand Miradov, Onal, Terlixis, Tarhan, Air, Zahika, Kemp, Heaney, Harwood, Urakov, and finally, Shavkat Tionov. This is the best moment if you want to take a picture. Huh? You can take a picture if you want. We have a little bit of time. All good for the bronze medalists? If you did not receive a bronze medal, please raise your hand. And if you have your flag, lower a bit your hand. There are... Everyone has received his or her, its gold medal? Yes? Bronze medal, sorry. Congratulations to all of you. The photos are taken. All good. You can please rejoin your seats. Thank you very much, and congratulations. Now, to give the medals to our silver medalists, I call on stage Pierre Chavel and Paul Stanley.
Plateau par plateau, photo par photo, on fait une photo, ils se mettent dans le coin pour faire la photo finale avec tout le monde. On fait une photo par...
Noted. Noted. So, the process is the same. When your name is announced, you can join us on stage, and this time, when you receive your medal, you go on the side so that we will join for a group photo, but when you receive, then you go here. Noted? I think yes. For our silver medalists, the names are Zai, Yann, Valérie, Rodríguez de Acevedo, Machado Feltrán, Evers Cordeiro, Brandao Suto, Young. I will just wait for this first slide of medalists. All good. Li, Huang, Tian, Kudrna, Kubika, Ranut, Polma, Pablo. Same process, I will wait a bit. I think we can continue. Gaillard, Chartoir, Ekstat, Leung, Toff, Teti, Shah, Gupta. Still with the silver medals. Zarabi, Sadeshinejad Simaki, Mohammadi, Golabdar, Gashai, Rutman, Moses Zvi, Lanis. You can come up over here. Yes, perfect. We continue. Ben Israel, Dorazio, Itami, Idonuma, Yelubai, Azat Bekov, Young, Razbadaukas, okay, they're getting fast. The next silver medals are for Yuknevicius, Runner, Sekrieru, Graur, Gourbazar, Erkembayar, Reukowskis, Plastzinin, we can go on with Kuznetsov, Kleukin, Rukovchuk, Krivoshekhov, Tudose, Mendelssohn, Kondrea, Sirokaran. Our next silver medalists are Alsaks, Popovic, Dromniakovic, Wee, Teng, Tan, Eng, Markovic. The next silver medalists are Hauk, Wang, Ho, Tanapitak, Anfon, Kakamiradova, Aisenem, Kakamiradova, Mariban, Vrashuk, we continue with Ostrovsky, Lavrenyuk, Fedirko, Tiwari, Sodi, Trong, Tran, Nguyen. And we continue, and I think we finish, yes, with Lee. Now is the moment to take all the pictures. We will wait for all our silver medalists to take the pictures. Congratulations. All the pictures done? Yes? Congratulations to our silver medalists. Finally, it is time for our gold medalists. A truly phenomenal accomplishment. To give them their medals, I call on stage Alain Aspect and Rajdeep Singh Rawat. Les médailles sont ici.
Is it possible to call in 2 batches of 20 each rather than all 40 together? And because otherwise some people behind at the back, they cannot get the picture.
With the gold, it will be possible. Are you ready for the gold medalists? Let's go. I call on stage. Ta-da-da. Zhu. Yang. Tong. Ling. Guo. I now call for our gold medalists. Dong, Kiao, Liu, Fu Bill, and Fu Seho Edison. Still for our gold medalists, Jia, Jain, Bendale, Hart, Sato. I now call on stage Kakutani, Amada, Lee Hyuk-jun, and Lee Yeon-ho, Han, and on stage, yes, yeah, I will call you, I think, just Choi, Lukin, Greshkin, Aronov, Stan. I now call Theo, Erman, Tsai, Su, and Ho. And they are fast with the gold medalists, so we can call Muizika Sopon, Zhang, Yevtushenko, Wang, Lee, and I also call Joel and Nguyen. All our gold medalists have been called. Time for the pictures. You can come with maybe all the flags on the same row. I think it's manageable with a picture from afar. Or stay like this, as you like. Okay, 20 seconds to take your last picture. But I know it is important. One last time, let's say congratulations to all our gold medalists. Thank you very much. You can now, go back to your seats and congratulations. So, I see that Alain Aspect, you want to steal a gold medal, yes?
Yes, I get one.
So congratulations to all our medalists and honorable mentions. This year, in line with France's strong commitment to inclusion and promoting the place of women in science, we are proud to introduce new special awards. The first is the Claudine Herman Prize for Best Female Performance, honoring individual brilliance. Claudine Herman was the first woman to hold a professorship at the École Polytechnique. She campaigned fervently to encourage young girls to take up scientific careers. To give this award, I call on stage Sophie Rémy and Danielle Rouen. Was the first woman to hold a professorship at the École Polytechnique. She campaigned fervently to encourage young girls to take up scientific careers. To give this award, I call on stage Sophie Rémy, Danielle Rouen. And the award goes to suspense. Kakamiradova Aisenem. Congratulations. Congratulations to Kakamiradova Amselem, and she has lots of things to bring home. With it will be hard. Maybe we need to help her to go back on to her seat. Congratulations. Perfect. Congratulations. And now, to encourage the importance of practical application and discovery, we have the Etienne Guillon Prize for the best performance in experimental examination, sponsored by Jane Street. Etienne Guillon was a physicist specializing in fluid mechanics. He was the director of the École Polytechnique, and he was a strong advocate for experimental practice in physics teaching. To give this award, I call on stage Alain Aspect and Daniel Rouen once more. He is already here. The prize goes to Stan Yonut Gabriel. Congratulations, Stan Yonut Gabriel, with also lots of things, yes, to bring back to your seat. Congrats. On we go with the next special award. For the mastery of abstract thought and complex problem solving, we present the Pierre Gilles de Gennes Prize for Best Performance in Theoretical Examination, sponsored by SquarePoint. Pierre Gilles de Gennes, winner of the 1991 Nobel Prize in Physics, insisted that mathematics should not overshadow physical phenomena. This prize highlights your capacity for reflection, abstraction, and modeling. To give this award, I call on stage Swan Piatecki, the head of product management at SquarePoint, and Yannick Almeras. And the award goes to Tong Pengyu. All good for the pictures? Yes, congratulations once again to Tong Pengyu. Finally, for the overall highest score, the ultimate recognition for outstanding achievement in physics, we have the Claude Cohen-Tanuji Prize for the absolute winner, sponsored by Cube Research and Technologies. To give this award, I call on stage, I will first explain who was Claude Cohen-Tanuji. He was awarded the 1997 Nobel Prize in Physics for his research in quantum mechanics. He warmly supported physics competitions for young and bright minds such as the IPhO. To give this award, I call on stage Ferdinand Tomarcio, the CEO of Cube Research and Technologies, and Professor Rajdeep Singh Rawat. And the winner is Lee Hyekyun. Congratulations, and I think, Mr. Tormacchio, you would like to say a quick few words to our absolute winner. Congrats. The mic is not working, maybe we can fix that.
Is it working? It's working. Thank you.
Fixed.
I'll be quick, don't worry. I'm very glad to be here because when I look around the room, I can see future researchers, physicists, inventors, maybe future Nobel Prize winners. But above all, what I see is something that unites us all across countries, across cultures. It's the language of science. It's something that we all have in common. It's a way of thinking that's both analytical and creative. And it gives you the power to understand the world, but also to change it. As a wise man once wrote, with great power comes great responsibility. So I think some of them, yeah, Stanley, Spider-Man. So please dream big and use these talents well. And congratulations again to all of you. Thank you.
Thanks a lot. Beyond the competition, the IPhO is about intellectual curiosity and cultural exchange. As so, we are delighted to enjoy a performance by someone who beautifully combines science and art, exploring the latest neuroscience discoveries on how the brain works and questioning our perception of reality. Representing the Cerebrum Theatre Troupe from the École Normale Supérieure de Paris-Saclay, please welcome Yvain Juillard.
Microphone? Okay. Good afternoon. Okay. So, how was your day? Great, I think. Can you all hear me? Yes? Even at the back? Okay. So, let's start with a little experiment. Louis, can you light the cube, please? Can you stare at it? Do you see a solid cube? Yes? In 3 dimensions, floating here? Can Everyone see a solid cube? It's actually a hollow cube. But if there is no shadows inside, you see a solid object. Even if the information it receives is incomplete, our brain always creates the most coherent image. You see a solid cube, you're sure of it, because most of the objects that surround us are solid, and especially cube. Except in this case, our brains are mistaken, all of them at once, as this cube is hollow. One of our brain's most remarkable properties is, without a doubt, its ability to put ourselves in a box. The hate, emptiness, and the unknown. But before, thank you, Louis. But before I go any further, I would like to propose you another experiment. And for this experiment, I need to divide the audience into two groups. The middle, it's here. Everyone on this side, close your eyes. Okay, close your eyes. The rest of you keep your eyes open and look at what is being projected. Now, those of you who had your eyes open, close them. And those of you who had your eyes closed, you can open them. Look at what is being projected. Now, everyone, close your eyes. And when I ask you to open your eyes, you will read the word you see out loud, nice and loud. Okay? Read it out. The first group here was given the context of these words. The second group was given these words. Depending on which context your brain experienced, the same word was interpreted in two different ways: live or leave. What does it mean? Every context we find ourselves in, or that we are put in, condition a certain interpretation of our realities, without our even being aware of it, and eliminate all other possible interpretation that can be useful to know. And what will be particularly difficult this afternoon, but essential if we want to gain a deeper understanding of how our brain works, will be, first of all, for us all to agree on the notion of reality. Because we use the word reality to describe a few different things: what we feel, what we see, what really exists. But what is visible? It's what really exists materially. Or is it merely a representation, a translation produced by our brain, which, as we have seen, can be played with? It can be fun, distorting the image we see. And what is matter? Matters as you know, is made up of extremely small components called atoms. An atom is a nucleus orbited by a cloud of electrons. To give you a sense of scale, if this chalk represents the nucleus of an atom, and we place it in the middle of the French Stadium in Paris, the electron orbiting it will be grain of sand in the car park outside. Matter is 99.9% empty space, but we do not see that empty space. You're not falling through your seat. The forces that maintain the cohesion of the elementary particles that make up the atoms in matter are strong enough to maintain the structure of the objects around us and of ourselves. But I'm not really touching the ground, and you're not touching your seat. So if we do not see what is really there, empty space with particles moving around in it, what do we see? What is this image that you have in front of you right now? Our brain, like our stomach, feeds on its environment, and it really does. But what it eats is much smaller. Light waves, sound, vibration, sand molecules. It's like a whale feeding on microplankton in the vastness of the ocean, except that our brain has several mouths of 5 senses. Right now, for example, your brains are downloading me. Thanks to the light waves that are bouncing off me and entering your eyes at speed of 300,000 kilometers per second. Thanks to the sound vibration that my vocal cords and my resonator are sending toward you by making air molecules vibrate against each other to hit your eardrum at speed of 340 meters per second. The photosensitive cells here in your retina chemically digest light vibration. The ear cells in the inner ear chemically digest the sound vibration, transforming them into electrochemical impulses that zip along the fascicle of your brain, crossing your synapses to be integrated in your memory, which gives them a new nature, that of a visible image, a sound, an audible sound, which we see, we hear, we are conscious. And that reality that our brain creates, it feeds on it once again to construct our memory, allowing us to maintain connection with one another and what we are, and between what we were and what we are. So our brain feeds on infinitely small elements all around us to produce something quite different in nature, something perceptible that we call our reality, and it keeps a trace of it in its memory. Immanuel Kant called everything that exists, that you study, noumena. It's what you study. And he called everything that our brain produced phenomenal reality. And that It's what I study like artist. It's images, sound, emotion, thoughts. So many realities, so many individual, so many interpretations of the world. So the word reality will be used this afternoon in a very specific sense, meaning phenomenal reality that our brain creates by feeding on noumena. Thank you very much.
Thank you, Yvan Juillard, for that thought-provoking performance. Now we continue with 4 prizes given specially this year for this IPhO 2025 edition in France. First, as mentioned earlier, France has made a strong commitment to promoting a more inclusive science, more diversity, not just in terms of nationality, but also gender. This is why we are delighted to recognize the 4 best gender-balanced teams which exemplify this commitment. To introduce the teams, I invite Sven Korving, postdoctoral researcher at the ITER organization.
Hello, everyone. I will try to keep it short with some introduction. First, I'm happy to see so many young future researchers here at the Olympiad, both young men and women. Today, I'm addressing you on behalf of the Director General Pietro Barabaschi of the ITER organization. I hope some of you know or have at least heard of ITER, but let me introduce. ITER is the biggest international science project in the world. But what do? We're building the largest tokamak in the world to show that nuclear fusion can be used as a sustainable energy source. Why nuclear fusion? The fuel is practically limitless. It's safe, non-carbon emitting, and no long-lived radioactive waste. It sounds amazing. But material does not want to fuse so easily. Of course, we all know, for this reason, we need smart physicists all like yourselves. Of course, we all know the sun. And some people have said, we're building a sun on Earth or a sun in a bottle. However, the sun can sustain itself because of its huge mass. It's gravitationally confined. On Earth, we cannot do this. We need to make something smarter and more efficient. We build a magnetic cage in the shape of a donut. There we heat a gas, a plasma, to 170 million degrees, 10 times the temperature of the sun's core. For this to work, we need smart physicists. But at the time of ITER's conception, no one country had the knowledge and industry to build ITER. It is a project situated in the south of France. However, it is shared among 35 countries all over the world. It's a very diverse project, both in topics and in people. And it's important, may I even say necessary, to include equality and diversity in our core values. And there, in ITER, there's equality between the nations and genders, where we all contribute and share our knowledge and know-how. For this reason, we have decided to grant an award to the team that encapsulates the greatest diversity. So maybe if we can put on the screen, there were 4 of the greatest diverse teams, if it's there. I don't see it yet. Oh, you have them. So this was.
4 teams are Turkmenistan, France, Azerbaijan, and North Macedonia. You can please come on stage right now, these 4 teams.
Yes, applause.
Please come, please come. We'll have a few pictures.
Yes, we'll take a
Yeah.
few. I will come and take a few pictures.
Yeah, and then you can continue. All good for the pictures? Congratulations. Okay.
However, you are all extremely great, but I am only allowed to give one prize of ITER to the best diverse country. And this was Turkmenistan.
Congratulations.
Not only do I congratulate you with this great achievement, but we welcome you, the participants of Turkmenistan, to come, all costs included, to visit and tour the ITER site. And you're welcome to come here and learn about the state-of-the-art nuclear fusion version in the world. Thank you.
Congrats. Thank you, Sven Corving. Thank you to the 4 teams. You can please rejoin your seats. And congratulations. You can please. I will just wait. We now have an award for the best total score by a team from the European Union from CNES, the French National Center for Space Studies. To present this award, I call on stage Pierre Tréfouré, Director of the President's Office.
Ladies and gentlemen, dear members of the judging panel, dear participants, first I must apologize for my French accent, which unfortunately is not part of the prize. It is a great honor for me to represent François Jacques, Chairman and CEO of CNES, to represent also the French Space Agency. Since its creation in 1961, CNES has been committed not only to space research and innovation, but also to promoting scientific culture and inspiring young minds. The 55th International Physics Olympiad, the first ever hosted in France, is a remarkable success. Physics plays a central role in meeting tomorrow's challenges, and CNES is very proud to support this prestigious event and the brilliant young talents gathered here. I am especially pleased to present today a very special prize, a parabolic flight, operated by our subsidiary Novespace. It offers short periods of true weightlessness, an extraordinary way to explore physics beyond the classroom. And the prize is awarded to Yonut Gabriel Stan, whose scientific curiosity, talent, and rigor truly impress the judging panel. Dear Yonut Gabriel, this flight is more than a reward. It's a step into the world of space and a rare opportunity to feel the laws of physics in action. I hope it fuels your passion and encourages you to pursue science with even greater ambition. On behalf of François Jacques and all of CNES, I warmly congratulate you and I wish you a fascinating and unforgettable flight. Thanks.
Congratulations. I have the feeling I have seen you multiple times today. Next, we have a special announcement from a leading institution in higher education in France and in the world, the ENS, École Normale Supérieure. Please welcome Professor Frédéric Chevy. He is there.
Okay, so I hope you guys enjoyed your stay in this wonderful city of Paris. I just would like to announce that for those of you who would be interested by coming back, ENS will organize a program following the lead of our mathematician colleagues, which is, can we show those slides? In which we will offer two scholarships for silver and gold medalists. This is a 3-year scholarship where you will be able to come to ENS to study up to the master degree. And this program will come with a few perks, including an access to a sponsored housing, student housing, which you will see is pretty precious in Paris. And also some flights, some tickets for flights to back home. So if you are interested, the program will start this year. The call will be open this fall, so around October. And if you're interested, you will get more information by flashing the QR code here. Thank you very much and see you very soon back in Paris.
Thank you, Professor Chevy, for this wonderful opportunity for silver or gold medalists. We'd also like to acknowledge the contributions of our partners in setting innovative challenges with a prize offered by Thales, world leader in high technologies for defense, aerospace, cybersecurity, and digital sectors. Here to say a few words about the Thales Solidarity STEM for All Award Special Prize for the IPhO is their representative and chief scientific officer, Marco Herman.
Hi, everybody. Really a pleasure to be with you today. And just in a word or two, STEM for All is a prize we deliver in Thales to students, early students, below 20 years, which you are, which embark on the science and physics, on STEM, which stands for Science, Technology, Engineering, and Mathematics. And we actually offer €5,000 support for those that are, in need to have some boost to start their career, plus additional 1-year mentor, which from Thales, which will follow the students. And we are delighted to be able to select, together with the organizing committee, 5 candidates for this STEM, which will be awarded today. But it's a special prize because the prize, they will enjoy it for 1 year with the mentor that will follow them. And they have been absolutely outstanding.
Do you want to announce the winners? Should I? I will announce the winners. Akinpelumi Samuel Opeyemi. Anna Gurdov Nurgaldi. Calderon Alba Carlos, you can come on stage. Ayman Fatima. And lastly, Tran Letien Nan. Congratulations. If you want to take a picture with the Thales representative, very quick. Very quick, yes. And then, I'm sorry, but we are limited on time. Congratulations to our 5 winners. I invite you back to your seats. And thank you, Marco Ehrman. It was the last prize of the day. Congratulations to all our winners. Now, all good things must come to an end. And as we say, don't cry because it's over, smile because it happened. One of my favorite moments of the opening ceremony was when the previous host country, the Islamic Republic of Iran, officially handed the IPhO flag to the new host nation, France. It is always heartwarming to see countries with different cultures, different traditions, share common ground peacefully and with a lot of mutual respect. To close the loop, it will soon be time for France to hand the flag of the IPhO flag to the next host for the next edition. And I am incredibly excited to announce that the IPhO 2026 will be hosted in the vibrant country of Colombia. Let's watch a short video about IPhO 2026 Colombia.
The Antonio Nariño University is proud to announce that Colombia will be hosting the 56th International Physics Olympiad from the 4th to the 12th of July, 2026, and welcomes all the participants of IPhO 2026 to the beautiful city of Bucaramanga. Bucaramanga, the city of parks, is the capital of the region of Santander. Located in the northeastern part of Colombia, Santander is known for the Chicamoca Canyon, historic cities, Big Bottom Dance, cacao and of course coffee. With climates ranging from moorlands to very warm and humid conditions, it is one of the most versatile regions in the country. In the last 40 years, scientific research in Colombia has flourished. The Antonio Nariño University, through its high-energy physics research group and other initiatives, has established a small and well-defined set of programs and projects, earning it first place in the rankings in the physical sciences in Colombia in 2025. The university, with the help of its partners in the region, look forward to hosting IPhO 2026 and welcoming all of you to Bucaramanga, Santander.
Congratulations to Colombia. I now call on stage the three French representatives, Julia Roussel, Dominique Aubert, and Pierre Chavel, along with Claire Bisquer, to hand the IPhO flag to the Colombia representatives, Fernando Vega Salamanca y Elena Patricia Lozada Falk. You can go. Congratulations to our Colombian friends for that exciting glimpse into the future. And now, to celebrate, we turn once more to music. We welcome again the association connecting scientific institutions through music. But first, someone has to speak.
So if Claire and Julia can come on stage, please. We are physicists. We know how to organize events. We have organized many events. First of all, we have classrooms every day. We have physics topical meetings every once in a while, of all kinds of meetings, small, medium, larger. But an event like this one, that's something special. We can do a lot in preparing it. We do not have all the skills needed for this kind of an event. So it takes professionals of event management to organize it. And that's why all the organizers of IPhO 2025 and the French Physical Society had the honor and the pleasure to hire professionals of event management. So please come on stage and let us applaud Claire and Julia.
Congratulations. Congratulations. And now it is time to welcome the association connecting scientific institutions through music. You have guessed it, it is the orchestra of the Plateau de Saclay. Thank you to the orchestra of the Plateau de Saclay. So what could we do while you clear the stage? Last time we did a wave. Let's do something else today. Let's do a clap. It's not a social experiment this time, I promise. We don't have time for that. We'll do a clap because they were so good. We'll start very slow and go faster and faster, okay? Everybody ready? When I clap, you clap. 3, 2, 1. Perfect, perfect. Now, I know you want to go to the cocktail. So do I. But we have to thank the volunteers for their enormous job, and also we have to thank the organizing committee. So I invite them to go on stage. No. I do not invite them. I do not invite them. I do another social experiment. What could I do? Okay, I'll try something else. It's a social experiment from Bobby McFerrin. You know Bobby McFerrin? The one who sings Don't Worry, Be Happy. I'll do a very short experiment because we have low time. Ready? I need your energy here. Huh? Bum, bum. Louder. Bum, 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 bum. Congrats. This is just the beginning of an experiment to show that music is a common language, something we talked about a lot. Now, I think it is time. The stage is clear. I can bring up on stage all the volunteers. Yes, they are here. Perfect.